Today we're going to learn about something called the rule of sum. The rule of sum states this: if one mutually exclusive event can occur in m ways, and a second event can occur in n ways, then one or the other, or inclusive, can occur in m plus n ways. Now, we really have to see that in action. So, if two events are not mutually exclusive, if they share an event, so if I was to draw a picture that represents non-mutually exclusive events, that would be it. The principle of inclusion and exclusions need to be considered. So include it, add it together, and then exclude this middle because we didn't want to double count it. And then finally, here's another little rule. To reduce the calculations, consider using the indirect method, which involves subtracting the unwanted events from the total number of outcomes in the sample space. So we have NA equals the total in the sample space. Subtract what is not A, the number of ways. So, example 1. Let's see how to do this. At the Winter Olympics, 24 or 25 countries may be participating. How many ways are there to arrange the flags? So I can either arrange 24 flags, 1, 2, 3, ... 24, 25, right? Or I can arrange 1, 2, 3, ... and only 24 flags. If 24 are participating, I do 24. If 25 are participating, this is 25 different ways to arrange it. None of these intersect. These two groups are mutually exclusive. So basically what that means is I can add the number of ways to arrange 25 flags and then add the number of ways to arrange 24 flags. Okay, so 24 factorial, right? So if I have 24 spots, 1, 2, 3, ... 24, 23, and 24, well, I can arrange one flag this way, the other flag, 23, and the remaining flags, I have 22 choices, ... which is 24 factorial. We multiply that. And then if I have 25 flags, that's simply 25 factorial. And so that's the answer. There's quite a number of ways. So that's scientific notations, 1.613 times 10 to the 25. So 25 decimal places, or 26. Because having 24 and 25s are mutually exclusive events, you can add the number of outcomes. Okay, so we explained that earlier. Now, question 1b with a twist. At the Winter Olympics, 7 or 8 countries, this is another example, 7 or 8 countries may be participating. How many ways are there to arrange the flags if the host country must be in the middle? Okay, so you might think it's the same, 7 factorial plus 8 factorial, yeah? Except we have to consider that it's in the middle. If 7, the host country should be in the middle. So let's just pretend there's 7. Let's take a look at that. 1, 2, 3, 4, 5, 6, and 7. Now, what does that mean that the host country is in the middle? It means that the host is in the middle, which means I only have 6 countries over here to choose from. 6 flags to choose from over here. Then once I choose the first, I have 5, 4. I'm going to put H right there. 3, 2, 1. So, in fact, that's 6 factorial. Well, what about 8 countries? And what does a middle mean in 8 countries? So, by the way, if there's 7 flags, that's automatically a different arrangement than if there's 8. So they're mutually exclusive. Oops, let's not get confused. 1, 2, 3, 4, 5, 6, 7, 8. Okay? it could be the case that the flag, the host country, is here. In which case there would be how many more flags left? 7, 6, 5, 4, 3, 2, 1. Right? So that's 7 factorial. So we had 6 factorial. Then we had 7 factorial. But it could also be the case that the host country, let's see this again, 7, 6, 1, 2, 3, 4, 5, 6, 7, and 8. It could be the case that the host country is in the middle right here. And every time the host country is in this position, that doesn't intersect with any of these, because that would mean it was over there, right? So if I specify it's H, therefore I have a third case where it's 7, 6, 5, 4, 3, 2, 1. I have 7 choices. So what ends up happening is, let's clear our markings. I have 6 factorial plus 7 factorial plus another 7 factorial, which makes it 720 plus 500. By the way, 6 factorial is 720. And then 7 factorial is 5040. And then this is from 5040. At which point we got 10,800. Because they are mutually exclusive events, you can add the number of outcomes, okay? So we explained why they were mutually exclusive. Now, we're going to try the principle of inclusion and exclusion to this. So 3 players receive 1 card each from the deck of cards, right? We're going to count. Now, 3 players receive 1 deck. In how many ways could the cards all be all face cards or red cards? Now, if you remember, okay, there's hearts, diamonds, they're red. And then if I remember correctly, let's try and get this to work. Then there's also clovers, or clubs, and spades. And for each of these, there's kings, queens, and jays, and we call those the face cards, right? So let's take a look at that. Okay. Well, how many ways are there to select face cards? How many ways could the cards be all face cards? So let's see. We'll divide it. How many ways can they be face cards? Well, there are 12 face cards. We're choosing 3. That's how many ways there are. That's basically 12 factorial over 12 minus 3 factorial, if you remember from the last, which is basically 12 factorial over 12 minus 3 is 9 factorial, which is equal to 12 times 11 times 10. We don't need to go over everything, which is 1320. Okay? Okay, so how many ways are there to select red cards? Well, there's 26 red cards, half the deck, and we're going to choose 3 of them. And if we do the math, that's 15,600. Now, P26 choose 3, that's basically 26 factorial over 26 minus 3 factorial, which is equal to, just to do the math, 26 factorial over 23 factorial, which is equal to 26 times 25 times 24. And then 23 times 23 factorial, which is 23 times 22 all the way down over 23 factorial. And we cancel that out. And that ends up becoming 15,600. Okay, so what next? So we have our numbers. What next? But face cards and red cards are not mutually exclusive. Okay, we know there's some intersection. we apply the principle of inclusion and inclusion, which is n, a, or b, which is face cards or red cards, equals n of a. By the way, this is, well, we'll call one of them n of a. We'll call this n of b. But what about n of a and b? How many of ways can we pick red face cards? How many ways are there to select 3 red face cards? And the answer is, well, how many red face cards are there? 6. And how many ways are there to choose? 6 choose 3. How do you do that? 6 factorial over 6 minus 3 factorial, which is the same thing as saying 6 factorial over 3 factorial, which is the same thing as saying 6 times 5 times 4 times 3 factorial over 3 factorial. Boom, boom. 6 times 5 times 4, which is equal to 120. Just showing you how to do the math really quick. But we don't need that for the sake of this. We just need the principle. Okay, so the number of ways to choose 3 face cards, by the way, this would be n of a and b. So it would be 12 choose 3 plus 26 choose 3 minus 6 choose 3, which is 16,800 ways to choose 3 cards and have it be all face cards or red cards, right? And remember, we did this minus 120 because we double counted it. We counted it here and we counted it there. Now, arranging letters. How many ways can the letters factor be arranged so that the vowels are not together? Well, there's so many different possibilities. Now remember before, let's see. Let's go back. I wish there was a way to go back easily. And going forward is going to be, there we go. No, where are we? Oh, this thing right here. Let's erase. Let's clear markings on this page. This thing right here, we're going to use it. Reduced calculations, consider using the indirect method, which involves subtracting the unwanted events from the total number of outcomes in the sample space. Let's move back, see what we're talking about. And why. We're going to talk about why that's important. Okay, so how many ways so that the vowels are not together? Well, A and O can be not together in a lot of ways. How many of ways can they not be together? There's a lot of ways to not be together. So 1 letter apart, A and O, right there. 2 letters apart, A and O right there. 3 letters apart, A and O right there. And by the way, it could have been F, A, C, O. Oh, that's not 2 letters apart. T, O. Could be 2 letters apart over here as well. 4 letters apart. Then switch the A's and the O's, right? Because we had A there, O there, etc. And we have 8. Now we have to find the different permutations for each of these 8 situations. That's not fun. So what's more fun is to use the indirect method. Or not fun, but easier. And how many ways can the letters factor be arranged so that the vowels are not together? Well, we can ask them. There's only 2 ways they can be together. Okay, how many ways are there to arrange the word factor? Total number of ways, no restrictions. 6 factorial. Why? Because I have 6 letters. F-A-C-T-O-R. And I have, this could be F, A, this could be 6, 5, 4, 3, 2, or 1. And that's equal to 720 ways. Okay? And then we say how many ways with the vowels together? Well, if we put them together, that's much in the same way we talked about with the picture of football players and junior football and senior football players being on the wall together in previous examples. So how many ways with the vowels together? 5 factorial, right? Because now A and O are considered one letter. So F, A, O. C-T-O-R. There's 5. 1, 2, 3, 4. Oops. And 5. And then multiply that by the number of ways we can arrange A and O, which is where we get the 2 factorial from. And then there are 720 ways in total. 240 ways to arrange factor where the vowels are together. In the remaining ways, the vowels are not together, so there are 480 ways to arrange factor without adjacent vowels. Okay? And this is your homework, and that's the end of